from Barcelona, in Catalan.
Awesome. So thanks a lot for joining us and telling us about your work with DRAID.
Thanks. Okay. So first of all, who am I? I'm Mateo from Barcelona. I'm Catalan. I work for Nivisis MP Store, which is a Sanmina company. Then I'm product owner for cold storage solutions. I'm also software development manager and cloud architect, and I help the business. Okay, feel free to add to me to LinkedIn. I wanted to do this. I wrote yesterday. So, can I see the comments because of my notes? Oh, I see. We only have one screen.
I can probably change it if you want. Let's see. All right, now we're going to real experimental territory.
Wait a second, grab my laptop, see the notes from there, and watch the screen.
It might actually work. Let me just. I just need to change this here. So now. Oh, I see. I need to move the window over there. All right.
Looks great.
Is this kind of what you're expecting?
Yeah, that will work. Can you make it bigger?
I don't know about this slide. Maybe you can drag this thing.
Oh, slide 2. Okay. No, it's fine. Perfect.
Is that okay?
Yeah.
Okay.
I think it will work.
All right. Let's make sure. Forward, backward.
Yeah. It works.
Oh yeah. Great. Okay. Sorry for the interruption, everyone. We're ready to resume.
Okay. The talk will last between 10 and 20 minutes. And we will cover basically rebuilding with the RAID with a spinning drive, not TCD. It's different modes. Okay. Okay. The RAID is a project that is still work in progress. It's a very promising technology. In my company, we wanted to see how far we can go. So here we will cover how did we get to understand the technology and what's the speed that we can get from it. I will use this, C for pointing the number of VDEPs, D for pointing the data strips per stripe, P for parity, and S for spares, which are distributed spares, not physical spares. Okay, the drives we were using for those tests were 4 terabyte Seagate SAS drives. Those drives were performing at 200 megabytes per second for read and for write. You can get that speed or checking back with DD, like inputting from deep zero to the device directly with a large amount to prevent the cache from the operating system, or doing things like generating a big random file from that random, for example, and then copying in a RAM drive, and then from there overwriting the device directly. That's to avoid like using that random, which is slow. So we pre-generate that on a RAM drive, and that will make it very fast. Or reading directly from the device to dev null. Okay, other tests confirm the same speeds, like FIO, etc. It's important not to use zeros. I use that for sample because I was accessing directly the device. It's okay, you can overwrite with that, but not with ZFS. because you can have different results. We are using for this HBA controllers, so not any kind of cache, just directly attached to the system. And this speed will be for the drive, but obviously as we creating a RAID system, that will be aggregated and we will have more speed. Okay, which servers we were using for that? We're using the 4U60. It's a 60 drive in 4U. This had a more or less powerful CPU, Intel Xeon, $2,500 per CPU, and 64 gigabytes of RAM. Controller was SAS2 with a max bandwidth more or less of 3.8 gigabytes per second. And we use another server, which is 4U90, that has in 4U 90 drives. The CPUs in here were cheap. I call it crappy, but it's not that polite. But were 400 each. And the RAM of the system was 120 gigabytes. One interesting thing of this server is that we had 4 SAS3 controllers, and each had a max bandwidth that should be 6.8 gigabytes per second. So the aggregated bandwidth of the system is more than 30 gigabytes per second. So we had zoning configured in that. So each controller had visibility to between 22 and 25 drives. So we maximize the bandwidth in this case. Okay, what were the challenges? The first challenge was totally internal, was understanding the technology. RAID 6, RAID 5, all those technologies has been there forever, for years, but the RAID was something completely new. We had to understand it. So what the RAID does is it uses a small fraction on every disk to provide distributed spare across all the drives. So when one drive dies, you can rebuild using those small fractions and aggregate the bandwidth of all the drives. So you avoid like the limit of the speed of one drive. That case, 200 megabytes per second, you can use the bandwidth aggregated of all the surviving drives. So the theory was and is the most drive we use, the faster the rebuild will be. We have some constraints, like the performance of the IOC and the number of them. We had to ask the question of what was the importance of the CPU in the rebuilding process. It's critical. We can use those cheap CPUs. We need like super powerful CPUs. So at the beginning, CPU really seemed to be very, very important. Then we discovered something, which we discovered is we had the RAID, the backend enabled. So we were wasting a lot of CPU, like just printing. So basically, we were tracing the system and seeing what was the waste that the CPU was wasting the time in what. So we saw those prints basically. So it was fun to discover that. Okay, it was a challenge for the company to understand how that technology compared to traditional RAID system, like 8+2, RAID 6. So the beginning was very disappointing for me because I was forced to use the RAID configs with 8+2 spares. So I will explain and you will understand why that doesn't make any sense for the RAID. Okay, the parameter you can disable if you want to disable the debug is the RAID _debug _ level. Well, you have to set to the, you can set different levels, so totally disable it. We also played with many parameters while we were rebuilding and learn about it. But we didn't get an improvement of that, maybe 1 minute or 2, which is not significant. We repeated the test many times, and sometimes we can have variance of 2 or 3 minutes. So 1 minute or 2 is not relevant. And which, for doing this, we had to fill the pools, which was something really slow with so many drives. And it helped something that is use the parameter ZFS dirty data max. Thanks, Richard, for that. That really helped reduce the times. Okay, so basically, how long it takes to rebuild a drive, what we call in ZFS resilver in a traditional RAID 6 system. Within the RAID and that 4 terabyte SAS spinning drives at 200 megabits per second, it was taking more than 9 hours on the 4U90. So basically, how it works is it has to read from all the surviving drives, all the information from all the drives, and then reveal the parity, so the data that has been lost, and then write to the new drive. So we have to read all the drive completely from all the drives, and then have to completely write this new device. So it's very slow. Why in this case, one BDEP with 8+2 distributed spares in the RAID was not bringing something spectacular? So basically because we had to read also from all the drives, all the content. I will introduce here the concept of ownership of data of the drives. Later I will explain a bit more. And you have a constraint on the spinning drives. You can read or you can write. If you in distributed RAID, sorry, in the cluster RAID, you read from all and you write from all. So you cannot do both at the same time. Okay. So for the test, we were filling the pools at 70% of data because ZFS is amazing and will only reveal the actual data, which is really an advantage. So to make these comparisons fairly, we fill to 70%. Okay, how we unblock that situation? As I explained, the filling the drives, 90 drives server is really, really slow, to 70%. Oh, yeah. So, and the servers were always busy with this config. We were trying this config, and it was really frustrating, trying to make something from this with the RAID when you know that it uses all the drives and the bandwidth, and the more BDEPs you have, the more speed. But we had to do that. So basically, patience, more patience. And then we were running rebuilds. At 10% fill, we run the rebuild. At 20%, at 30%, at 40%, then releasing the spare all the time. So that way we managed to know something very interesting, that the rebuilding times were linear, more or less. So given that you know that the time for 5% rebuild, you can approximate very well, very accurately, 1 minute, 2 minutes up, down, or like that, but you can approximate very well. And you can know also the reading bandwidth, the writing bandwidth. So we got very nice information from that. And again, more patience. And at some point, some tests finished. So I grabbed the servers one weekend and decided to try the things I wanted to try. So I tried the things that were important for this. Okay, so I destroyed the pools. I was hating these pools. And I created a config that I wanted a quick win. So I went for the maximum number of BDEPs, not caring about data efficiency in this case. So I created a config of 29 BDEPs of 2 data strips plus 1 parity strip per stripe, and 3 distributed spares. I fill it to 70%. It was 73% in this case, but something interesting that came is like filling it was much more faster than with the previous configs. And then I removed 1 drive and did the RAID rebuild. And in this case, it took only 37 minutes, which was something interesting, given that clients from the company were reporting like times around 1 week or something like that. So, okay, with RAID 6. Okay, you have to take in account, and even if RAID 6 pools are not very big, like 8+2 or 10+2 or alike. All the drives are sharing the input-output controllers. So the bandwidth, you are limited by the bandwidth. So if the RAIDs that are healthy are being accessed and read by a lot of users, the bandwidth you have for rebuilding is also reduced. So that will increase the time. So you have to take in account the bandwidth your server or your JBot has. That's important. Not only the time for rebuilding, because other users will be accessing the server in other ways. Not necessarily by 1 gig card. Maybe your server has 100 gig cards, or 40 gig cards, or 25, or 10, whatever. Also, I did several tests that weekend with several configs, and what I saw is that the smaller the data strip is, the faster I was able to access the data and to write and to rebuild. Later, much more data confirms all of this. So the funny thing is that when I showed these results to the execs, they say, "Okay, let Carlos work. He knows what he's doing. So don't disturb him." That was nice. You have been there, all of you. So okay. Okay, so I wanted to just show a video.
Let's see how we do that. So we have to there. And then,
okay. You can go back to the notes. No. If not, I will explain later. No worries. Was displayed. Okay, no worries. I will explain. I'm sorry. Sorry for the poor quality. In the laptop was okay, but
the projector.
Or maybe is getting from Google Drive. Okay, what we have here is a Grafana with all the drives, taking the bandwidth of all the drives during a rebuild of a config of 8 data strips, 8+3 parities. I think it's 5 VDEPs. In my notes, I will check. And that's the that's the bright bandwidth that it's using for rebuilding, and that's the read bandwidth. On top, sorry, it's not well displayed, but on top it's 2.5 gigabytes per second. We were reading an aggregated speed of something more than 2 gigabytes per second. And we were writing at around 300 megabytes per second, combining all the speed of all the drives. But the good thing of that is that each drive has to write few information. So it's not the same to write 3 terabytes to one drive to write few gigabytes to several drives. And that's how it's so fast, because you write small information to each drive, small amount of information to each drive.
I need to do it with speaker notes. Oh, this
I think it was okay.
Well, when I do this, you get this, but then no speaker notes over here. Is there a button there? Is there another button there? Great. Yeah. I want this window over here.
Cool.
All right. Good. Excellent. We figured it out. Okay. There you go.
Good.
Sorry about that.
No, it's fine. Thanks, Emilian. I don't see my notes here.
Oh.
I don't see my notes.
It should maybe. Oh, there you go. There's the notes on this slide.
Oh, here. Okay. So the config I was showing here was 5 times 8 plus 3 plus 3. Using parity 3 is something that I really like, especially when we have so many drives. For this test, we allocated 400 gigabytes of real data, which is 550 gigabytes with the parity blocks. And it was rebuilt 9.38 gigabytes of data. So 9.38 gigabytes of data split across so many drives is why it's so fast. Okay, so what we learned from this is that basically the rate is a trade-off between the number of bits and the speed. So where in a RAID 6 system you have 1 8 plus 3, for example, or 5 8 plus 3 rates, we aggregate that. So we still have 5 8 plus 3, but in a single pool. So the more data stripes per pool we have, the more speed we will have. That also means that we sacrifice more drives for speed, more parity drives for speed, and more spares. But again, it will be the same if you have like 4 RAID 6 pools. So it will be the same, and this time really much more faster. Okay, and like in the RAID, all the surviving drives contribute to the write bandwidth, creating that distributed spare across all the drives. And all the surviving drives will be read, but only the part of the data that they own that is required for rebuilding. So the more bits we create, the smaller fraction of data that we will need to rebuild the data from the missing drive. So if we use C times 16 plus 1 plus whatever spares, we will have 16 surviving strips that will be read in order to rebuild 1 strip. If it was like 8 plus 1, only 8 strips will be read. That means that whatever combinations, like 7 of data and 1 parity, or 8 data, whatever, because we can have lost data on parity. And the same for 2 plus 1. In order to rebuild just 1 data strip, data or parity, 2 of the blocks will be read. Okay. I will explain how the distributed spare works. It's a simplification. And in order to do that, I use the most simple configuration, or one of the most simple configurations. Okay, so basically we have 8 drives. And the data strips, data and parity, whatever, doesn't matter, are distributed. When you use the RAID CFG, it creates a mapping of that in order to try to configure the drives. So when we use it, all the drives will be used, the most approximate to the ideal situation. So basically, it's like they are randomly distributed. And the S1 and S2 refers to the on-format space that has been kept on the drive for rebuilding with the logical or distributed spare 1 and the distributed spare 2. So I will show now how it works. Now we are gonna kill one of the drives. Okay, so drive 3 is lost. We have lost that information, or it's simply removed. So we see that for this data stripe, we have the 3 blocks, the 2 data and the parity. But for this, 1 is missing. This is the one that we have to rebuild. In here, we have the yellows, 3 yellows, okay, but for the orange, okay, we have 3 as well, so that's okay. That will not be used. 2 blues and 3 green, so we need to rebuild 1 blue. So then, okay, sorry. Then we do the RAID rebuild, and in the space that was reserved for the distributed spare one, we have rebuilt the red block that was missing. No matter if that was data or parity, it's put in here. Here we didn't need it because we had the 3 oranges and 3 yellows. And here, same. Sorry. Here we had rebuilt 1 blue block on the S1, and that's it. We could do the same with the second spare if we lost another drive. So so the key in here is that we have regained full redundancy very, very fast. That's the idea. So be safe, that the pool is safe as soon as possible. Obviously, we want to replace that drive. So at the end, it will be a resilver going on. But for now, we have our parity restored. Something which is cool in this case, I like this example because we only had 1 parity, but we have 2 spares. So we have lost 1 drive, we have rebuilt, we regained that parity, that safe condition. So we can lose another drive and use the second spare to rebuild. So we can afford to lose 2 drives, even if we had only parity 1. Okay, so that's a graphic that shows how impacts the rebuild times. The resolution has lost a lot, but with a RAID 6 traditional technology and DRAID, the blue is DRAID. So when we add more drives, understanding that we are more VDEPs, we are adding more VDEPs, we are cutting the times. That's the hours, number of hours. So from 5, we are going down to around 30 minutes or 25 minutes ideally. But with the same situation, if we try to do a big, very big pool with RAID 6, like instead of 8+2, like going like 30+2 or 60+2 in this case, we are using 60 drives. So if we go, the time is more and more slow. And you say, okay, but you have the time to write is always the same because you put a new drive. Yeah, the time to write is always the same, but you have to read from very long strike to get the parity revealed. So that's the opposite situation. That's also related with the ownership of data of the drive. Okay, those were the rebuild times for a config of C8+2 spares. This was the ideal time or the simulations, what we calculated. The red is the 4U90, which has 90 drives. That's 92. And the yellow is the 4U60. That's why it stops in here, because it has no more drives. Something interesting is that from the theory to the reality, we found some differences, and digging. One of the things that we found is that you cannot read and write at the same time into the same drive. I mean, so that makes some difference because between the theory and the reality, but it's very interesting. Also, in this case, we are using this config. Other configs take more advantage or more speed or less time. Other configs may take more. So depending on this config. Okay, so I wanted to show the spreadsheet now. Let's see if we can Sorry.
All right. Is this okay, or do we need to change the resolution?
Cool. Okay. So we did several tests like to show that. I have picked the ones that are more relevant. Initially, we had that config that was basically a plain 1 VDEP 84 drives plus 3 of parity, very long, plus 3 spares, so distributed spares. And we filled to 70%, and we did a rebuild. and it took 19 hours and 34 minutes. I have cut the seconds in here because it doesn't matter. Sometimes it goes up or down 2 or 3 minutes or 5. So depending on the time, so seconds doesn't matter. So the interesting thing in here is the average rebuilding speed, which was like 44 megabytes per second. And that was the config. For 90 total drives, 1 VDEP, 84. So it's very difficult to show like that. Can we get to the initial state where we have the full resolution? Or even if I lost the notes, it doesn't matter. It's difficult to do this. Sorry for that.
That's better. There's another window. Okay. Good.
Okay. So something interesting in here is the total number of data drives, the total parity drives, and the data efficiency. So how many real data you can put in that pool. The usable capacity. And also when I was rebuilding, I was running, well, me and my team were running IOStat in order to know exactly the bandwidth that we are having. And in this case, it's interesting to see that we had 5.4 gigabytes per second of bandwidth for reading. And then we were writing an 89 megabytes per second, which is really low, but for that config makes sense. Also for filling, we were filling at 521 megabytes per second. That's according to IOStat. And the total speed for data was 261 megabytes for data, megabytes per second.
So what's the difference between write and filling?
Well, when you fill the pool, you fill the usable capacity. But when you write, you are writing to data strips and parity strips. So you are always writing to more drives that real data is available. But I will answer all the questions later because it's advanced matter. It's many questions will come. We are almost there. So from that initial point of having just 1 VDEP, we started to break in more VDEPs. So we did in this case a 4 VDEPs of 20 plus 2. That was not with the initial release of the DRAID, because the initial release of the DRAID only allow power of 2 for the data strips. So that will cause kernel panic. Later, Isaac pushed another version that allow us to do that. So for this config, rebuilding one missing drive, it took 4 hours and 9 minutes, which was better. And the data efficiency was still good, with 80 data drives and 8 parity drives. The usable capacity is according to the data drives. So the bandwidth for read was 7.4 gigabytes per second, and again, writing was not brilliant. And when we were filling, we were using 2.2 gigabytes per second according to IOStat. Okay. So please note that in this case, the D or the data strips per stripe was big, so 20. When we reduce that number, like in this case, like 8, things go much more faster. So it makes sense because in this case, to rebuild one parity block, 20 drives have to be read and calculated. But in this case, it's only 8. Okay, so with this config, we got 2 hours and 24 minutes. The data efficiency was much more lower than in this case because we were sacrificing 15 drives of parity for this, and also having 5 distributed spares. the read bandwidth was good, and writing was better. So what we will see is that writing will be better and better. So the I/O, the input-output operations that we can do will be more and more, and everything will be faster and faster when we reduce the number of data strips to write. So this config is very similar. Instead of using parity 3, we are using parity 2, and instead of 8 drives, we are using 9. It got a very similar time. All of these tests were with the 4U90. In this case, we did the same test with the 4U60, and we got something interesting. Even if the input-output controller was SAS2 and not SAS3, and we had only 1 and not 4, like in the 4U90, we got a small reduction in time, which seems to be related to the parity calculations and the fact that the CPU was very, very powerful. It's not important. We are talking about 4 minutes in this case, but it's significant to understand, okay, it's worth for me like to invest like $5,000 in very good CPU to reduce 10 minutes. Maybe it's, or maybe it's not. When we are talking about 2, 3, 4 hours of rebuilding, perhaps 10 minutes is not that important, and the price of the hardware it is. So it's a balance that every company or every person has to decide. Another config we reduce a bit. We use 6 data strips per stripe and just 1 parity, and that was much more faster. We got 1 hour and 20 minutes. The data efficiency was good in this case, and we can see, we can see that when we were writing, we were using 3.5 gigabytes per second. That's very, very nice writing speed. And that comes better and better when we reduce the number of data strips per stripe. So in this case, we got 7 VDEVs of this config and 9 VDEVs, and we didn't get a very big improvement. Something that is a bit counterintuitive is that in order to cut in half the time, we have to multiply per 2 the number of drives. So really jumping from 7 VDEVs to 9 VDEVs doesn't make a big difference. It will make a big difference if we have, with the same config, 14 VDEVs, but that's a lot of drives. So in order to cut in half the rebuilding times, more or less in half, we have to double the number of drives with the same config. Okay, so that's more interesting for I/O. 14 times 4 plus 1 spare, we got 51 minutes. Everything was filling at 70%. So for the notes. And writing in here, when rebuilding, we were using 1.6 gigabytes per second and 7.6 gigabytes per second for reading, which is nice. And finally, that config, that was the initial I was testing, the best time we got was 25 minutes at the end. And that's something very interesting. We use, in this case, 29, it's in here, 29 parity drives. So from 88, we're using 29 for parity, plus 1 for the spare. So the data efficiency goes down, but you get a very, very nice writing speed, reading speed, and rebuilding speed. So for applications like video or things like that, you can afford to have a config like that. You need a lot of space. These are super expensive. That can bring something interesting to you. Okay, that's it.
We're almost out of time.
Yeah. Okay. Okay. So we are almost there.
Maybe I'll just
Okay.
There you go.
So that's basically the information. First of all, well, thanks to all of you for being here and for listening. And I wanted to give a special thanks to all the team that has worked in this investigation. Sean, Kevin, Sheila, Delo, Dean, Elham, Frank, Jason, Kais, Richard, Rick, Ben, Alejandro, a lot of people has helped to get there. And it has been very interesting journey, and a lot of nice conclusion has come. So that's it. Feel free to contact me through any question or whatever. And do we have time for?
I think we're running a little bit behind, so maybe we'll hold questions for now. But during the hackathon, we're also going to have some like breakout discussion sessions. And one that we've been planning yesterday was to talk about DRAID.
Yeah, of course.
So,
yeah, please.
why don't we say folks that have questions about DRAID and this talk, we're going to have a breakout probably in that room right there during the beginning of the hackathon. So thanks a lot.
Oh, thanks a million.
Yeah.
Thanks, guys.